Hi everyone, and in this video I'm going to be talking about uncertainty principles in math, specifically in Fourier analysis. And I'll be talking about briefly the Heisenberg uncertainty principle and how to formalize this in the context of Fourier transforms, and from this an extension due to Hardy, which now bears his name. So first I want to describe the setup. So I'll be working over the reals. So I'll be considering usually measurable functions, L1 functions in particular, from R to C with respect to Lebesgue measure, and I'll be using the convention that the Fourier transform is... My X's are not that great, but if we're regarding it as something on R instead of Rn, all this goes through for Rn up to some constant factors. I'll just do it for R for simplicity. My convention is that we're integrating over R f of x e to the negative 2 pi I cx dx. And the properties of f and f hat bear certain relations. And in particular, we can think of the Fourier transform as exchanging smoothness, regularity, and decay. And the Fourier transform can be defined in a fairly high degree of generality, for example, over locally compact abelian groups, where all of this makes sense with respect to Haar measure. But we're going to make it quite concrete. And again, there are versions that hold in a more abstract setting, but we're going to work over R. So the Fourier transform exchanges smoothness and decay. And there's a couple of ways that we can make this precise. So one such way is that it preserves the short space, which consists of functions that are smooth, and it consists of functions all of whose derivatives, including itself, decay faster than any polynomial. So these are sufficiently regular in that they're smooth, is the best we can get, and they also have rapid decay. So the Fourier transform, which swaps smoothness and decay, preserves the space because they're both smooth and decay fast enough. So this is the theory of Schwartz functions. If we have that hat maps L1 functions to functions that vanish at infinity, which I'll denote by C sub 0. So functions in L1 are almost continuous in some sense, and they map to functions that vanish at infinity. This space contains, for example, as a dense subspace, compactly supported continuous functions on R, and so on and so forth. And the theory of these functions is quite nice. They have the dual space of such a space can be described, and so on and so forth. It's a very interesting function space. Okay, here's another one. If f is compactly supported, well, let me just say f is in here, then f hat is entire, and this is going to be a function on the complex plane, its extension, with at most exponential growth. And this is the most closely related to what we're going to be doing today. There's other properties that we could mention, Plancherel's theorem, which is that it affords a unitary automorphism of L2, it's a Hilbert space. In particular, the L2 norm of f and its Fourier transform are equal. And we also have the fact that if f is exponentially decreasing, it's analytic in a strip. So this is another thing that relates the decay or the way that f behaves at infinity with regularity of its Fourier transform as a function of the complex plane. So in particular, it's holomorphic in some strip. And this is a nice theorem. So this last one is called the Paley-Wiener theorem. And it has a number of very interesting variants which you can look into. But this is not exactly the focus of the video today. I want to formalize the relationship that f and f hat can't both be heavily localized. It can't. They both cannot be like super concentrated up. If one of them is heavily localized, that is, it looks like some kind of like point mass at zero, then its Fourier transform has to be extremely dispersed. It has to be something that doesn't peak sharply. So another way to phrase this is that both cannot decay too strongly at infinity in some way that we want to quantify. And we can make this precise via the Heisenberg uncertainty principle, which is crucial and is the stepping stone that we need for the Hardy uncertainty principle, which refines this. And I'm not going to prove it. There are various references that do so I'll just state it. So theorem Heisenberg uncertainty. And I just want to mention that you might have heard of this from physics, and the intuition there is that you have these operators that correspond to, I think, it must be momentum and position operators, and these cannot both be localized in the sense that under the Fourier transform you have that multiplication by xi corresponds to differentiation with respect to c inside the integral. So the Fourier transform makes this precise if you're looking at this opera theoretic formulation, and there's a way to translate between the physics and the math here. So in purely mathematical terms, if we have the L2 norm is equal to 1, hence the L2 norm of its Fourier transform by Plancherel so if we normalize, then I'll just write out this whole quantity. You can write this more succinctly in terms of L2 norms. This whole thing over here write the Fourier transform there. Is greater than or equal to 1 over 4 pi squared. Let me move this recording. There we go. Yeah, so we can bound it below. It has to be greater than some fixed constant. So this means that at least one of f and f hat cannot be too concentrated near 0, and we can also translate this so that we can, instead of all these x's, we can have like x minus a for some real a. So it doesn't really matter. This is translation variant. The proof of this is not super tricky. You use Plancherel at some point. You integrate by parts, and you use certain tricks or identities, and then you have to bound using Cauchy swords, and so it comes through. So now I'm going to talk about the Hardy uncertainty principle, which in the classical setting says that the fastest that f and f hat simultaneously decay, we can ask the following natural question. What is the fastest that f hat can simultaneously decay? And the answer, as I was going to say, is given by the Hardy uncertainty principle. So theorem. So if f is measurable with the following bounds, it's bounded by some multiple of some Gaussian, and so is its Fourier transform. Let's write negative pi squared over a for all x, c, and some constant c, c prime, a positive, then f is actually forced to be a multiple of this very Gaussian, so e to the minus pi ax squared. This is a really nice result. So it says that if you have sufficiently rapid decay for both the function and its Fourier transform, it's actually forced to be a Gaussian or some multiple of it. Okay, and we proved this using the methods of complex analysis, and we're going to use a certain principle called the Fragment-Lindelöf principle. This is not a particular theorem, but it's a class of results that generalize Liouville's theorem to getting bounds on non-compact regions. Or, sorry, not Liouville, I mean maximum modulus, to non-compact regions. And a classical case is the three lines lemma, where you have bounds on two vertical ends of a strip, and you can bound it uniformly inside the strip by some interpolation. Okay, so let's give a proof of this result. We can assume that a equals 1, because we can just dilate or contract by square root a, or 1 over square root a. And we can also multiply by some small constant to assume that c equals c prime equals 1. So we have this normalization. This doesn't change anything. Because f decays faster than the exponential, we can extend f to some, sorry, f hat to the complex plane by stating that f hat of some complex number c plus I eta is the integral over r of fx e to the negative 2 pi xc e to the 2 pi eta x dx. And this makes sense. Given the rapid decay, this thing does not explode. So, turns out that, as we discussed above, this f hat is entire. on C, so it's holomorphic everywhere. And this is because you can essentially use the niceness of f to differentiate under the integral sign, and then we see that this thing is actually complex differentiable everywhere. Okay, so we can obtain a crude lower bound by taking absolute values of both sides. So in particular, I'm just going to copy paste this whole thing. This is purely definitional. If we have absolute values, then we can take the absolute value in here, bound this above by everything in here, 2 pi eta x, sorry, yeah, that's right, dx, whoops, that would change this, so then we have, this is equal to, this is equal to 1, so this whole thing is just integral over r, e to the negative pi x squared, e to the 2 pi eta x dx, and we can remove the absolute values because these are just, these are real. Okay. So now we can complete the square. And we obtain the following bounds. This is less than or equal to e to the pi eta squared. So this is for all xi and eta. Then we're going to define this new function f of z by e to the pi z squared times f hat of z. So now for z equals I eta, purely imaginary, f of z equals e to the pi, negative pi, eta squared, f hat of I eta. So by the above, f of z is bounded in magnitude by 1 for imaginary part. Z, sorry, the real part equal to 0 for all z on the imaginary axis. Okay, so we have a bound on the entirety of the imaginary axis for this new function. And moreover, by hypothesis on f hat, we have this is bounded above by 1 on the real axis. So now we have bounds on the real axis and the imaginary axis, and we would like to bound this on the entire complex plane. So heuristically, now that we have bounds across both axes, we can extend these bounds to the entirety of the complex plane just by kind of interpolating between these two. But we can't just naively say this, so we're going to justify this claim. And now we want to show f is constant on C, from which the claim will follow, because big F is just, big F is just some Gaussian times f hat. So if this thing is constant, then the claim will follow that f and f hat are Gaussians. In particular, we have that f hat is Gaussian, so it's, I guess by using like Fourier inversion or something like that, we can just see that f has to be Gaussian as well. So that's automatic. Okay, so now let us justify this argument. This is a fragment Lindelof argument. So I guess the classical statement, at least according to the reference that I'm using, which I'll post, this is a nice blog post by Terry Tao, it uses exponential growth on the function in question, which you want to show as constant or you want to bound dynamically. In this case, we don't quite have exponential growth. We actually have faster growth. This is quadratic exponential, but we can modify it a little bit and then we can apply the classical principle. So we pick the sector 0 less than theta less than pi over 2. This is the angle, and then we pick the sector. Gamma sub theta, oh dear, which is all r e to the I alpha, where r is positive, and the angle ranges between 0 and this fixed theta. Okay, so now this is somewhere in the first quadrant, and we can just kind of use symmetry to conclude. So we're going to work with the upper right quadrant, and then we're going to just say that you can get similar bounds everywhere else. So this is easy because now we have bounds on the positive real and positive imaginary axes, and these kind of enclose the upper right quadrant, even if not strictly, because this is a non-compact region. And this is precisely the kind of interpolation principle or Fragment-Lindelof argument that we can use. I suspect there's a way using conformal mapping to reduce this problem down to some kind of like 3-line lemma argument, but this is elegant too, and we can just proceed as in the blog post. So now we have, recall that we have the bound over here, so I'll copy this. Which gives us the bound on big F similarly. Now if delta, we pick some small positive delta, and theta is sufficiently close to pi over 2 in a way that depends on delta, then this new function where we're introducing the small delta parameter, e to the I delta z squared, f of z. This guy is bounded in magnitude by 1 for z on the boundary of the sector. So this is some sector in the upper half plane. And we want to just kind of extend this throughout and take a limit as theta goes to pi over 2 and say that we still have this boundedness. And the way we do this is for any small enough epsilon, we can define this rather contrived looking function that actually turns out to be quite convenient, perfect with what we want. So this is e to the I epsilon. So we nest this, and this is e to the 2 plus epsilon times e to the, the same function above that we bounded on the boundary of gamma theta. So this is e to the I z squared gamma. Sorry, what am I saying? This is f of z. We can bound all of this, right? Because then this is just e to the I epsilon, e to the I epsilon. E to the I delta z squared. F of z is bounded above by 1 on this boundary, which is to say, on the real line for sure, we already know this bound, but also on the upper part of the sector, this ray that extends from the origin out from some angle of alpha less than, pi over 2. And we just pick the usual branch of z to the 2 plus epsilon, and this thing exponent is big enough. As long as it's bigger than 2, then this is fine. And within the interior of this sector, we have that the limit of, let me call this like g of z. As this grows arbitrarily large, and this is still within here, so we take this like radial limit outward. This goes to 0 because we have this term absolutely destroys everything. And we have that because this goes to 0 and infinity in the interior, we can use maximum modulus. This is honest maximum modulus as we're used to seeing in complex analysis. We can bound g of z by 1 in the interior of the sector. Now, we're going to let epsilon, of course, go to 0. And then we take this limit to pi over 2. And finally, we take a third limit. We let delta, this discrepancy between theta and pi over 2, to 0, which then controls this part over here, this factor, and this whole function, the bound on this, we have that f of z is equal to 1 for all real part of z, imaginary part of z. It's greater than or equal to 0. So on the closed upper right quadrant, and then by symmetry, similar arguments for the other quadrants. So by Liouville, f is constant. And we're done. Great, so this is a nice illustrative principle about the behavior of the Fourier transform and how we not only have the Heisenberg uncertainty principle, which tells us that we can't simultaneously localize a function's Fourier transform, let's say an L1 function. The Hardy uncertainty principle tells us a slightly sharper fact that if you have sufficiently fast decay of fn's Fourier transform, then it actually has to be up to some scalar multiple, a Gaussian. So it's a very prescribed form. And this is nice because we know that Gaussians are, in some sense, the most tractable or the most accessible form of Schwartz functions. They certainly decay faster than any polynomial, and derivatives don't do anything to that because you're just differentiating an exponential. And these are as smooth as you can get. So these kind of look like little bumps or peaks near the origin in Rn. And yeah, hopefully you enjoyed watching this video, and I might follow this up with some things in the future. Thanks for watching.